All right, so working on the rest of this review, now we're writing each complex number in polar form. So a reminder that right now the complex number is in rectangular form, where we have a and b. And polar form is sort of the unsimplified one. So this is going to be z equals r times cosine theta plus I times sine theta. So we need to figure out r and we need to figure out theta, and then we just write this kind of ugly formula. So r is the Pythagorean theorem. Negative 4 squared is 16 plus 4 radical 3. When you square that, that's 4 squared is 16 times radical 3 squared, which is 3. So this is the square root of 16 plus 48, and that's 64. So r is 8. And then theta is always found using tangent. Tangent of theta is 4 radical 3 over negative 4, which is negative radical 3. Now, tangent is negative radical 3 at two different angles, right, in quadrants 2 and quadrants 4. And you could use either one, but depending on which angle you use, you're changing your r from positive to negative. So what I like to do is plot the complex number. If this were the complex plane and this were the real number plane, we would go left 4 and up 4 radical 3. So because we're in quadrant 2, I'm just going to give the quadrant 2 answer for theta. So what is theta in quadrant 2? Let's see. We are at pi over 3, right? Because here's the pi over 3 angle. Tangents, radical 3 over 1. And so in quadrant 2, that's 2 pi over 3. So our answer for this one is z equals r, which is 8, because I'm facing quadrant 2, so I'm going forward 8. And then cosine of 2 pi over 3 plus I times sine of 2 pi over 3. And that's how we leave our answer. All right. If you chose, what would this be? 5 pi over 3 in quadrant 4, then you would need to have r be negative 8 because you're facing the wrong way and walking backwards. Same idea for this next one. So we have an a and a b. This is in rectangular form. So the first thing is to find r by using Pythagorean theorem. So if we square root of 3 over 16. Now, I don't really care what 16 squared is, because remember, you're just going to be taking the square root of this. So save yourself time and just make this 3 over 16 squared. And then we're adding to that, because we're squaring this, another 3 over 16 squared. So that is radical 6 over radical 16 squared. So radical 6 over 16, which doesn't simplify any further. And then when we have theta, we're going to do tangent of theta is negative radical 3 over 16 divided by radical 3 over 16. A number divided by itself comes out, in this case, to negative 1. And again, which quadrant are we facing? So for this one, you would go right radical 3 over 16 and then down radical 3 over 16. So because we're in quadrant 4, we should be using the pi over 4 angle that's in quadrant 4. So theta is equal to 7 pi over 4. And then our complex number here is radical 6 over 16 times the cosine of 7 pi over 4 plus I times the sine of 7 pi over 4. All right, so when we write a complex number in polar form, it looks ugly. You don't want to do any of this math, because if you start doing the math, you would end up back where you started in rectangular form. Now, speaking of doing the math, that's what this last part is. So now write each complex number in rectangular form. So rectangular form is just z equals a plus bi. And so here we have the ugly polar form, and we just need to do the math. So I'm going to leave the radical 6 out here for a minute. 5 pi over 4 is in quadrant 3. So cosine of 5 pi over 4 is negative radical 2 over 2. Plus I times sine is also negative radical 2 over 2. Distribute the radical 6 through. So radical 6 times radical 2 is negative radical 12 over 2 minus radical 12 over 2 times I. And remember, we have to simplify radicals for our AP test. So z is equal to This is negative 2 radical 3 over 2. So negative 2 radical 3 over 2 is just going to be negative radical 3. And same thing here, minus radical 3 times I. So there's my simplified complex number in rectangular form. Another way to think about rectangular form is just that you don't want to have any trig. Get rid of the trig, get rid of the parentheses. Same idea for number 22. So we have 2/3 times the cosine of pi over 6. So that's in quadrant 1. That's radical 3 over 2. Plus 2/3 times the sine of pi over 6, which is 1/2 times I. And we just clean that up. So cancel your 2's, radical 3 over 3. Cancel your 2's here, plus 1/3 times I, or you could write plus I over 3. Okay, so that finishes our complex number section. And then the last thing that I have on here is a series of graphs. So I've given you a little bit of each. We've got 2 rows curves. Now we've got 2 of these where we need to just kind of make a table and plug in points. But remember, on the rows curves, you can use symmetry to your advantage. So we have 4 sine of 2 theta. So 2 theta tells me that's an even number. So we have 4 petals. The 4 that's out in front tells you the length to the end of each petal. And if there are 4 petals around a full circle 2 pi, if we divide that by 4, we can find that they are pi over 2 apart. Meaning from the end of each petal to the next, you should rotate pi over 2. And take a look at your graph right now. How many sections is pi over 2? So from 0 to pi over 2, that's like 3 of these sections. So sometimes I remind myself of that too, just so I don't place something in the wrong area. I'm still going to start by using a little bit of a table. But when we did these graphing worksheets, I did everything without symmetry in case any of you wanted to go that route. But after seeing you do your graphing worksheets, it looks like most of you are using symmetry, which is great. So that means that you really only have to get a couple of points on here. We always plug in 0. That gives me 4 times the sine of 2 times 0, which is 4 times the sine of 0, which is 4 times 0. Okay, so that doesn't really help us much for the end of the petal. We start at the origin. And then what do I need to plug in to get 1/2? Because when we have 4 petals, I do want you to accurately find the width of the petal. It's harder when we have 3 petals. These are our only 2 scenarios, by the way. So we want to know, well, when is sine of 2 theta equal to 1/2? And what I do know is that when I plug pi over 6 into sine, I get 1/2. So the question is really, what angle makes 2 theta equal to pi over 6? When we divide by 2, this is where this pi over 12 comes in. All right, so we need to be plugging in pi over 12 to get the width of the first petal. And the reason we do that, again, is because you're plugging into 2 times pi over 12, sine of 2 theta, not just sine of theta. And so, oh, this just crashed on me. Let's see if it comes back up. There we go. And so, oh, goodness, cut all that out. Okay, so when we plug in pi over 12, we get 4 times, like I said, 2 times pi over 12. Well, 2 over 12 reduces. That's 4 times the sine of pi over 6. That's 4 times 1/2, which is 2. Face pi over 12. I think that this is pretty easy to plot. You know pi over 6, so pi over 12 is easy to just mark off about halfway and walk forward 2 units. And then what's the other angle I want? Well, I want to know, when is sine of 2 theta equal to 1, because that's where you're going to get the end of the petal. And I know that the sine of pi over 2 is equal to 1. Oh my gosh, I don't know what's up with this crashing here. Let's see if it comes back. My computer is not happy with me. Okay, so I know that the sine of pi over 2 is equal to 1, and I know that I have sine of 2 theta. So if 2 theta is equal to pi over 2, I should be plugging in pi over 4. So let's plug in pi over 4. Again, that's going to be 2 times pi over 4. That's pi over 2. 4 times the sine of pi over 2 is 4 times 1, which is 4. So I face pi over 4, which again, you need to mark in here. I will use these same grids for the graphing portion of our quiz, by the way, just so you know that. Walk forward 1, 2, 3, 4. And at this point, I'm done with my table. I can use symmetry from here on out. I know that the other side of the pedal, the other width where we go out 2, should be halfway between pi over 2 and pi over 3. So I'm going to walk forward 2. So here's the first pedal, like this. Okay, and then what about the other ones? So remember, these are all pi over 2 apart. So use symmetry now. I do the pedal tips next. So pi over 2 is 3 full sections. So I'm going to go 1, 2, 3. Or another way to look at that is like I've got a pedal tip at pi over 4. So I'm going to have a pedal tip at every pi over 4 in this graph. So these are all the little pi over 4 angles in each quadrant. And then what about the width of the pedal? So however you want to do this, like notice that those are happening at the halfway mark between the axis and each like angle that's close to it. So you could also do that and say, okay, here I've got to go 2 forward. Here I've got to go 2 forward. So here's another pedal. I'm graphing these out of order, by the way. If I were to spirograph this, I would not be hitting them in this order. It would go like this. Do them in their correct order. And then we would dip down into quadrant 3. Oops, I went too far on that one. 2, 1, 2, right here. No, right here. Sorry. And then we would come back around to quadrant 4, and then we would end back at 0. Okay, so that is my rose petal. If you don't like that, then you can, if you want to just keep plugging away, you do need the table, like I did in some of the other worksheets, to write out all of the nice angles that you want to plug in for sine, and then set 2 theta equal to those angles to see how much you have to plug in. But it comes out to all the pi over 12s, all the pi over 4s, and all the non-quadrant angles. Let's do the same thing for 24. So for this rose curve, we have an odd number in front of our angle. So this is going to be 3 petals, and these are going to have a length of 6 to the end of a petal. And for the cosine graph, I'm going to do the same thing and say, well, for this one, the petal tips should be a full circle 2 pi divided by 3. That's how many units apart these are. How far is that? Well, here's 2 pi over 3. That's 1, 2, 3, 4 sections. I guess I should probably be calling them sectors, but whatever. All right, so if we put in 0, we get 6 times the cosine of 3 times 0 is still 0. Cosine of 0 is 1. So we face 0, and we go out 1, 2, 3, 4, 5, 6. If you've done enough of these now in the homework, you might have picked up on this pattern. You should notice that sine, a rose curve for sine, always starts in quadrant 1. The end of the petal starts there. And for cosine, the first petal, the end of that petal starts here on the x-axis every single time. And it's just because of where we put in 0. All right, so the next nice angle that I want to put in for cosine is cosine of pi over 3, because that gives me 1/2. But remember, for these, that means that 3 theta is going to equal pi over 3. So the theta I would need to put in is pi over 9, and I can kind of estimate where that is. Like here's pi over 9, and I'd be going out 1, 2, 3 units. But that's really not going to be easy to plot all the way around the circle. So I'm not too worried about that. The next thing I want to do is cosine of pi over 2, which is equal to 0. And that would be me plugging in, if 3 theta is equal to pi over 2, I would be plugging in pi over 6 if I solve for theta. So the next angle, if you are going to go with the table, is plug in pi over 6. You get 6 cosine of 3 pi over 6, which is pi over 2, which is 0. So the next point here, if I'm not doing petal width, is just the next point is just from here, the end of the petal, back to the center. And then let's just use symmetry instead of the table. I really didn't even need to plug in the pi over 6, because if I'm not having you do petal width, these are going to be pretty skinny anyway. Then all of these are 2 pi over 3 apart. So remember, we're saying, well, the next one should be at 6. The next petal tip should be here, and then go another 2 pi over 3 or another 4 sections. And the last petal should be here. So this graph does something like this. Remember these fill in, they rotate around like spirographs, so in a counterclockwise direction. So that's as much as you would have to graph for 24. All right, our last two graphs here are not rose curves. When you add or subtract a number out in front, that changes what's happening with the graph. So these could be cardioids or they could be lemicons with an inner loop. This is just a nice cosine theta. So I'm just going to start by plugging away with my angles. You should have in your head by now which angles are nice to plug into cosine and which ones are nice to plug into sine. So we have to start at 0, and then we get 1 minus 2 times cosine of 0, which is 1. 1 minus 2 is negative 1. So face 0 and go back 1. I would advise you to plot as you go, because if something doesn't fall into place nicely, you'll know you made a mistake somewhere faster than if you do the whole thing and then start plotting. Okay, our quadrant 1 angle that's nice for cosine is pi over 3. 1 minus 2 times the cosine of pi over 3 is 1/2. 1 minus 1 is 0. So it doesn't matter where we face, but sure, face pi over 3 and walk 0. So far we have this. We always plug in the non-quadrant angles, so plug in pi over 2. 1 minus 2 times 0 is equal to 1. And so we're facing pi over 2, and we're going up 1 unit. Okay, and then we're going to 2 pi over 3. And so we have at 2 pi over 3, we have 1 minus 2 times cosine of 2 pi over 3 is negative 1/2. That's 1 plus 1 is 2. So here's 2 pi over 3, and we're going 1, 2. We're going 2 units forward. Now this graph does look kind of weird, so either I made a mistake somewhere or I want to double check my work on this just to be sure. So 1 minus 2 is negative 1. Oops, yeah, see, I plotted my first point in the wrong spot. So that's why this looks so strange. I was thinking like, okay, there's no way this could rotate up here. So sorry about that if you caught that earlier. Wondered when I was going to catch on. My first point I plotted wrong, right? I face 0 and go back 1. This makes more sense. I can rotate this way and continue out. Okay. All right, so then let's plug in pi. That's next. 1 minus 2 times cosine of pi is negative 1. That's 1 plus 2 is 3. So face pi and go 1, 2, 3 units forward. Now you're here. Now you might be able to use symmetry at this point. This definitely has to be an inner loop type of lemicon, I think it is. But if you're not sure, just keep going. So plug in 4 pi over 3. 1 minus 2 times cosine of 4 pi over 3 is negative 1/2. 1 plus 1 is 2. Face 4 pi over 3, go out 1, 2. See how that's symmetric with the point up here. Okay, so now we're doing this. And then maybe this is enough for you to see where it's going to go, but we need to get back to this point. So if not, plug in 3 pi over 2. 1 minus 2 times 0 is 1. Face 3 pi over 2, go forward 1. Again, symmetric. Then you're going to do 5 pi over 3. 1 minus 2 times cosine of 5 pi over 3 is positive 1/2. You're back to 0. That's a bad connection there. Back to 0 like that. That's not much better. And then you're going to end here. If you plug in 2 pi, you're facing 2 pi, you're going backward 1. All right, last one. I changed this to negative 3 minus 3 sine theta. I think I did that for your packet, but just in case, you might need to make that adjustment. So negative 3 minus 3 sine theta. Now this is a sine function, so the nice angles are the pi over 6s and the non-quadrants. We have to start at 0. We get negative 3 minus 3 times 0 is negative 3. So let's see if I do this right this time. Face 0, go 1, 2, 3 backwards. Then we're going to plug in pi over 6. We get negative 3 minus 3 times sine of pi over 6 is 1/2. Negative 3 minus 1.5 is negative 4.5. So face pi over 6, but go backward 1, 2, 3, 4.5. There. Then pi over 2. Negative 3 minus 3 times sine of pi over 2 is 1. That's negative 6. So face pi over 2, but go down 1, 2, 3, 4, 5, 6. Or I should say go backwards, 6. Here's what we have so far. Okay, and then we're going to plug in 5 pi over 6. Negative 3 minus 3 times positive 1 half is back to negative 4.5. Excuse me. So face 5 pi over 6, but walk backward 1, 2, 3, 4.5. I'm going to try to round this out better for that little section. Okay, and then again, you could be using symmetry, but it's best to just keep going because you don't, this is one of those cardioids, but just in case, might as well just plug in pi. Negative 3 minus 3 times sine of pi is 0. Face pi and go backward 1, 2, 3 units. Okay, and then we're going to plug in 7 pi over 6. Negative 3 minus 3 times negative 1 half. Okay, so that's negative 3 plus 1.5, so that's negative 1.5. So face 7 pi over 6, but go backwards 1.5 units. And then we can plug in 3 pi over 2. Negative 3 minus 3 times negative 1 is negative 3 plus 3, 0. And okay, fine, maybe I'm convinced enough by my symmetry here to let this go. All right, that's our cardioid. So you can see we've just done 4 graphs. There are 3 graphs, I believe, on my quiz. So you can I'll leave you to guess about which 3 we might have, which 3 types we might have. But it comes down to you can always graph by just making a table, and you should have enough time for that. If you're worried about time, do the graphs first. All right, that's it for the review.